I think is it. First of all, what is this utility function? This utility function is refers to a criteria which is disturbance to the local people. Because when you build an hydropower plant, of course, you have the local people don't like it because it's noisy, and also it may impact on the landscape and etc. And therefore, you can define an indicator, a criteria, which is the disturbance of the local inhabitants. And in this case, here the utility is reported depending on an indicator which quantifies the disturbance. And of course, the indicator depends on the design flow. So, in this case, it means that if here you don't have the design flow, but rather an indicator, we have the design flow in our utility function. Here we have, rather than the design flow, an indicator. It means that in between you need a function translating the design flow to the indicator. And these functions are defined according to indications given by the literature. So basically you see here the value of the indicator, but indeed one could draw the same picture by putting the design flow here. And you see that the utility varies from 0 to 1, and you see that the change, the shape is nonlinear. And you may wonder what are these points. These points were derived by analyzing already existing plants. For these plants, it has been quantified the indicator, disturbance to local people, and according, through a consultation with the stakeholders, it has been assigned a utility. So basically, this professional engineer took data for all these existing plants, and for these plants he computed the indicator, depending on the design flow, and then he went there and asked people to rank the disturbance in a given scale. He used the same scale for different sites, and by interviewing a lot of people, he could get a reliable estimate of the utility. Because, of course, if you ask one person for a given plant, can you please tell me, in a scale from 1 to 10, what is the disturbance that you feel? And this person may say 8, and then you interview 7 of them. And then you get to an average indicator of disturbance, which may be 8.5. And then you do that for other plants, and then you may assign utility 1 to the plant where the disturbance was lower. Basically, you rescale the scale from 0 to 10. You rescale it in the range 0, 1. And he did this. So he went there, he visited about 10 existing plants, maybe some more. 1, 2, 3, 4, 5, 8, 10, 15 of them. He went there and interviewed a sufficient number of people. Sufficient may be 10, more than 10. And then he could define this. And then he was able to present to the stakeholders of the plant that was under design. He could present this utility function, and he would say, I interviewed the people for all these plants, and they told me that the disturbance can be ranked in this way. And indeed, the resulting shape of the utility function is reasonable. Now let's see some more. This is the disturbance to the wildlife, similar. And then this is the impact, the temporary impact of the construction works. In this case, he found a relationship that was quite linear, so he adopted a linear function. And you may say this is out of work for this poor professional engineer, but he really got a scientific paper because it was really significant. And it was published in a conference proceeding of an Italian conference, but it got a lot of attention because it was indeed a significant work. And this professional engineer decided to make this work because he's involved in designing a lot of these small hydropower plants, because he got a good experience with these plants. And I told you that these plants now are increasing in in terms of built plants, and therefore he felt that it was worthwhile getting a solid support to the choices that he had to make. And this is the result. I'm sorry it is in Italian because, you know, when you write papers dealing with scientific research questions, then the optimal arena is the international one. When papers deal with technical questions, usually people prefer the national context because, you know, the approaches to practical engineering strictly depend on the country, because they depend on the law in force, they depend on the environmental conditions. So the constraint that you have when you build such an hydropower plant in Italy are much different from the constraints that you get in Norway, for instance, in North Europe. It's a completely different story. So basically the technical experience usually is more nationally based. And also there is to say that typically, you know, in Italy at least, we are not used to speaking English, and therefore it's more likely to find English-speaking people in Italy in the scientific community than in the technical community. This is of course another reason. But in this case, it was not the language, the reason why we were motivated to write in Italian this paper. The fact is that we thought that this is a contribution that is better placed in the national context. So this is a suggestion that I give to you which has general validity. If you are dealing with a research question, the international context is the international arena. If you deal with technical problems, you have to look at the national literature, plus the international one, but you don't have to forget the national literature. While in science, nowadays people don't consider the national literatures anymore. Okay, so basically we have defined so far our utility functions, and then we have to move forward. Let me go back to R. Okay, so here we are. We have the utilities. Now we have to turn to the problem of defining the weights. Because of course, we now have the single utilities, we have to combine them. You remember that you need to combine the utilities that you got for each of the criteria all together through the weights that you must assign to each criteria. So now weight assignment is our problem, and in order to do that we have to perform our pairwise comparison. So let me start by looking back at the criteria, because if we have to compare them 2 by 2, we have to have clear in mind what they mean. So let me go back to the criteria. Basically, criteria 1 is economical benefit. Criteria 2 is species. And then there is landscape and tourism recreation. And now we have to build our matrix. So first of all, this is a 4 by 4 matrix, because we have 4 criteria. Let me write in R a 4 by 4 matrix. Let me create it. So let me call it, I use the same name for the variables that is given in the file that I provided to you. So I go back to the file to have a look what is the name. The name is Roma. Perfect. Roma means trial in Italian, as you probably know better than me. Because, you know, speaking well in Italy is not so easy, and even in Italy you don't find many people that speak well in Italian. And engineers usually don't speak well in Italian, so maybe that my Italian is not really the best one that you could take as an example. But there are some, this is just a parenthesis in order to chuck a bit. And the culture for the Italian language is rapidly decreasing. So basically there are old professors here, they are engineers, but they speak a very good Italian. And in my case I am in between. machine, and if you look at young people, the chance of getting people speaking well in Italian is much lower. And I think this is not necessarily a bad thing, because, you know, it's, I think that it's good to know how the language should be spoken, but on the other hand, I think it's an unnecessary effort nowadays to make the language more complicated, because usually the language, when it's well spoken, is complicated. So, let me close this parenthesis. This is my array. Array 0, which means that I put zeros for now there. I'm just defining it. Dimension equals C 4, 4. So now, if I display my array, that's it. Okay, so let me make the first comparison. First of all, prova 1, 1 is 1. No doubt on that. Now, prova 1, 2, which is economical benefit against fishes. So, let's try to adopt a conservative approach. Let's give the same importance. And so basically, no, the second one is economical benefit versus the fishes. Sorry? You mean 1 is economical benefit against economical benefit, is 1. Okay? The matrix is antisymmetric and it's diagonal. Okay? So basically, if I put a 1 here, it would mean that I give the same importance. We may say, let's try to get a conservative approach and say 1/2, which means that I care less the economical benefit with respect to fishes. Let's keep this in mind. This is environmentally friendly as an interpretation. And of course, if you ask the fishermen, they would say 1/9, and if you ask the manager, he would say 9 here. So let's say that we are conservative, but of course not very much, because if you want to be very conservative, we should put 1/9. Let's put 1/9. Okay. The third is, sorry, my memory is limited, is economical benefit against landscape. Okay. So we may say that the landscape, let's suppose that landscape here is not so nice. So let's say that we may say that economical benefit is more important. But still, we don't want to put a 9 because we are conservative, so let's put 5. And then we have economical benefit with respect to tourism. Okay, let's say that we were in favor of fishes, so we were in favor of more water in the river. And then let's say that we are also in favor of, again, more water in the river, which means more tourism. So let's put here 1/3. Okay. Now, 2-1 is simple. 2-1, as I said, is simple. It's 2. It's antisymmetric. Now, let me have a look at the matrix. Now, let me clear the screen. Okay, here is the matrix. So it's antisymmetric, so this is fine. And then 2-2 is again simple. It's 1. Perfect. Now there is 2-3. 2-3 is fishes against the landscape. We said that the landscape is not really important, so let's put fishes much more important than the landscape, 7. Because, you know, I admitted that fishes are more important than the economical benefit. And the importance of the economical benefit against the landscape was 5. So it means that I have to give a greater importance of fishes against the landscape, because fishes are more important than the economical benefit. The economical benefit is more important than the landscape. And all these reasonings are extremely important when you discuss with people. And in order to, you have to continuously issue call for coherency. Okay? In the same way I'm doing with you, we have to do with people. Okay, and now we have 2.4. 2.4 is fishes and tourism. If you remember our evaluation, basically we said that we concluded that tourism is a bit more important than fishes. And therefore here I should put fishes against tourism. Let me try with 1. Yes. Now, let me look at the matrix again. Okay, so 1, 3 is easy. If 1, 3 is, sorry, not 1, 3, 3, 1. 3, 1 is easy. It's basically 1/5, correct. Thank you. 3, 2 is again easy, should be 1/7. Yes. 1/7. 3, 3 is easy, it's 1. 3, 4 is to think about that. So 3, 4 is, just 1 second. Landscape against tourism. I think this should be 1/9 maybe. Let me try with this. Landscape, we said that it's something that we don't care about. Tourism so far was the highest rank in our classification so far. So basically let's say 1/9. I clear the screen, and here is the matrix. So now we have 4, 1, which is 3, I would say. 4, 2. It's the inverse of 2, 4. So 2, 4 is 4.5, so this should be 2. 4, 3. It's the inverse of 3, 4, so I think it's 9. And then 4, 4 is 1. So the matrix should be this one. 1, 2, 0.2, 3, 1, 5, 5, okay. And then I have 2, 0, 2, 1, 7, 0.5, 1. I think it works. 0.2. Yes, should work. Should be fine. Now let me compute. If I remember, this is the instruction. Let me check on the file that I give to you to see if I have the same symbols. Yeah. Okay, now we have to compute, to check the consistency, because I doubt that it's consistent. Maybe it's acceptable, but let's check. So I back to, I don't remember the instructions, so basically this is the instruction that we used last time to compute this should be the eigen, let me see what is here. Yeah, this should be the scaled weight. Yes, these are the weights. And basically, what you see here is consistent with our expectation, but still we don't know if the matrix is consistent. What you see here are the 4 weights, and you see a weight of 0.2, let's say, for the economical benefit, a slightly greater weight, 0.3 for the fishes, and this was to be expected, a low weight for the landscape, 0.05, again expected, and the highest weight for the tourism, 0.5. They sum up to 1 because I rescaled them. But still, as I said, we have to check consistency. And basically, what we have to do now is to compute the lambda. The lambda should be 4. And it will not be 4, it will be hopefully close. But let's see how much close is it. So I go back to the file where I'm getting the same instruction that I used last time. So basically, let me do this. Let me compute the maximum eigenvalue lambda. Not bad. It's 4.04. Which I think means that the evaluation is consistent. And the maximum eigenvalue, it's given by, they are the same value because the way in which I'm computing them, it makes a replication of the highest value, a replication of 4 times 4 lambda. So basically, I was expecting that they got the same value, and I was expecting 4, it's 4.04. And in my opinion, it should be consistent, but let's make a check. And in order to make this check, I have to go back, let me go back to the document that I gave to you in the previous lectures, where the check of consistency is explained. So let me go back to the document, just 1 second. I think this was the document, yes. Here we are. So now we have compute CI, which is basically the value of lambda minus 4 divided by 3. So let me make the computation. CI is equal to, we could, let me copy it. 0.041801 divided by 3. Basically, I took 4.04 minus 4 divided by 3. This is CI. And then I go back to the document. I have to divide CI times 0.9, divide by 0.9. So basically, I take CI divided 4.9, and then the resulting value is 0.01, which is much lower than 0.1. So it's fine. It's consistent. Okay, so now we have these weights. And let me call them back. We have these weights here. And we can use these weights to combine the utilities. let me find the resulting overall utility of the first alternative. So basically, what I could do is write U80 is equal to U180, sorry, U180 times BR2 1. There will be a quickest way of computing the overall utility for the 4 or 5 alternatives. I'm just computing them one by one because I want to be clear. And then we have plus U2 80 times BR2. And then let me copy this. U3 80 here 3 plus U4 80 here 4. So U80 is 4.45. Perfect. And remember that this result here cannot be greater than 1 because we are combining 4 utilities through the weights. So let's suppose that the utilities take all of them the maximum value. They take value 1. But then we multiply them for the weights. And the weights, they sum up to 1. So, of course, the highest possible result that we can get when computing the utility for each of the alternatives is 1. And you get 1 only if the 4 utilities for the 4 criteria are all taking the unit value. Only in this case. You cannot exceed it. And you cannot go below 0, of course, because the lowest value for the 4 utilities is 0. You don't have negative values. So when you combine from the weights, whose weights are positive, then at least you take a value of 0. Okay, now we can compute U90. And I can modify the previous computation. U90, U90. Unite. What is uniting? It's less useful. What's to be expected? Because we took a conservative approach. So for the same very reason, I am expecting now a decrease of the overall utility for increasing river flow. Let's see if this is true. U100. Good. U110. Good. U120. Perfect. So the best solution is 80. And probably, if we try the lower values, we may get higher utilities. This is not given for sure, because these utility functions are not linearly varying over the whole range of the river flows. they have overall, they have a nonlinear shape. So the fact that on one range of the possible alternatives, you have one criteria prevailing. So we identify that in the range from 80 to 110, 120, we have the criteria that tend to give, as a result, lower design flows, they prevail. And for this reason, you know, when you decrease the design flow, you get increasing utilities. But when the shape of the utility function is non-linear overall, because this utility function is done in this way, so you have linear change in the range 30, 150. But if you consider the whole range, this is non-linear. Non-linear because, you see, it's given by two segments which have different slope, and therefore here you have a non-linearity, a singularity. And therefore, when the overall range is non-linear, the fact that the criteria prevails in a range where the changes are probably all of them linear doesn't imply that the same criteria prevails on the whole range. So it may happen that when you decrease the design flow, you may try it. You get to a value where the utility, instead of increasing, starts decreasing, so reaches a maximum. And this is an experiment that could be done. In general, you know, there is a limiting value for the design flow of an hydropower plant. And a limiting value such that if you design a hydropower plant for a lower design flow, it's not convenient anymore, it's not worth doing it. So basically, the example that I made, where the alternatives basically are limited because there is a minimum value of the river flow is realistic, because it doesn't, it's not worth, you know, in many cases designing a hydropower plant for design flow that is very, it makes sense if the design flow is greater than a certain value. And you may say at this stage that in principle our utility analysis should tell us by itself if a hydropower plant is convenient or not. But indeed, this happens if you consider through this pairwise comparison and utility analysis all the indicators, so you get a comprehensive set of indicators, including the economical benefit, including the risk that you may take when running the plant, etc. So if you got indeed a comparison among a comprehensive set of criteria, then the analysis of the best decision should tell you indeed what is the limiting value. But actually, in many cases, you consider only a restricted number of indicators for simplicity, and also because the decision process becomes easier to explain and to carry out, especially easier to explain. And therefore, you may not consider some indicators that at the end of the story suggest to you that you don't have to go below a certain design flow. And as I said, this example is realistic, but still you may find, according to this example, that there is indeed a lower value for the design flow, even in this case. One should try, okay? So basically what I would like to do is, after the break, to try, with the same example, an approach that is less conservative with respect to the environment. And then we should see that we end up with the highest possible design flow. And, but before doing that, I would like to make a general consideration, to give some general thoughts on this procedure. And basically the message that I would like to convey to you, you don't have to necessarily assume that you always need a utility analysis and a pairwise comparison to carry out a decision like these examples that I gave to you. So the message is that these are helpful tools. They can be necessary to be used when the decision is impossible to carry out in a simpler way. But actually, the message that I would like to convey to you is that when you design everything, you should take the simplest way to carry out the design that allows you to reach the target. And why the simplest one? Because in practice you have to consider practical features of the design activity, which are the cost. So if you take the simplest way to reach the target, which means that your design is good, but you took the simplest method to get a good design, your work becomes cheaper, and therefore you are more competitive, and in general, the community takes the most efficient solution to reach the target. This is one reason. The other reason is that when the procedure becomes too complicated, you may end up with more difficulties in convincing the people that your approach leads you to the best decision. So decision theory indeed helps to reach consensus, but to reach consensus you also need to use a simple method. So the moral of the story is that you should use decision theory by taking the simplest method that allows you to reach the consensus. So at the end, you don't necessarily need to use these techniques. You need to use these techniques if you can find a simpler way to reach the consensus. But if you can't find it, it's certainly better that you reach the consensus by using the simple method. What are simpler methods with respect to this analytic approach? First of all, if you can reach the consensus by